is Jorik from the Groep. I work as an assistant professor across the street at the University of Amsterdam. And it's my great pleasure to introduce the next presenter. So the next speaker is Shuxia Tao from Eindhoven. And so she has a background in physical chemistry and came to the Netherlands in 2007 to start her PhD. And that's where she became an expert in computational material physics. And so in 2011 she got her PhD, and with a track record in material science for hydrogen storage for batteries. And then she went to NICAF, which is also right here. I guess you were based in Amsterdam for a few years. There you use your skills in materials design to design new photodetectors. And then in 2016, she started as a tenure tracker in Eindhoven. So I guess they must have missed you over those years. And there you managed to get 2 grants to get your group going. A tenure track grant, but also an NBO startup. And now you have a very successful group doing multi-scale modeling for energy materials. And so last year, or this year, you got promoted to associate professor, and also you managed to get a VD grant. So I think we are all very excited to hear what this is all about. So, the floor is yours.
Thank you very much, Erik, for this extensive introduction. So I like the speaker this morning. I don't make solar cells, the panels on the roof. I don't make solar cells in the lab, but I put material in computer, I simulate them. So you're going to listen to me a lot about atoms, ions, electrons. I hope that, yes, so that, yeah. All of them has to do with defect behavior in the new type of semiconductor in halide perovskites. Indeed, Jorik already gave you a very extensive introduction about my background, but I would like to go it again, but now putting it in the context of my field, my expertise. So in computational material science, you say that there are different skills. I started when I was very young in the DFT level, look at electronic structures. The field in the past 10 years has been developing so fast that there are many set of tools available that allow us to look at the complicated behaviors like dynamical behaviors, how a material responds to external stimuli, light, electrical bias. And in the past years, we also developed this expertise in the group. And indeed, we worked on a few different kinds of topics, crossing from chemistry to physics. And 5-6 years ago, I was start to establish my group. I was thinking, what makes me happy? I would like to look at chemistry, the physics, their interplay, but also something has societal impact. And then that's why I was lucky to find the perovskites. If you notice that you did plot, there's a small question mark here. So in these years, I did not do much. I did not publish a science or later paper, but instead I was busy with these 2 kids. And luckily, they share the same passion with us, with all of us. It's true. And you see in their hands these beautiful crystals. They are made exactly to the scale of 1 nanometer to 10 centimeters. And if you look at them, not only they are beautiful, but you can actually exchange the atom to different kinds of chemical elements that allow us to tune the chemical composition. A lot of interest in physics and chemistry also emerge from the tunability. What is most important for today is that these crystals also make a very efficient solar cells. So this is a perovskite absorber in the device. All of you a bit familiar with that. Indeed, we are lucky with this type of material. And even at the year when I started my career, I was very late to catch this trend. But the efficiency already almost went to more than 20%. But why I was still excited about it? Because there are the stability problems. The material are not stable, the cells typically last thousands of hours at that time. I think now it's much more improved. And indeed, we can tune the chemistry, we can make better films, and even we do that, if we zoom out, the cells only last a couple of months. Our group focused on these three very critical, very fundamental questions. One is why this material is so efficient to make solar cells, and then why actually it's not stable. And most importantly, how do we stabilize them? To tackle these three problems or questions, we use different combination of different computing tools, but we also quickly enough realized all of these questions are relevant to the defect in behavior. How to deform, how much are there, what are there, how do they impact the electronic structure, how do they impact the stability, and most importantly, how to get rid of them. So let's start with the first very fundamental question. Are the defects harmful for the efficiency? So typically we know that in this type of material there can be a lot of defects. Typically are characterized with either a missing atom or there's extra atom called vacancy or interstitial. And so this is use monthly as an example. And we're looking at how thermodynamically, how easy and how difficult such a species formed. If we get knowledge of that, we can also look at how this defect level are landed on the electronic structures. If in the band edge, they're not harmful, they can be thermalized easily. If in the middle, they cause our efficiency. To do that, we use the DFT calculations. Many of you knows a little bit what is DFT. What we do is we create a large enough cell, and we make all kinds of defects. You can see there are different pair of defects. And we make sure that we systematically look at them, the system of charge neutral, and we calculate the total energy of the pure, perfect and the defective lattice. And we also obtain the electronic structures. Don't be scared with this equation. Basically, what we want to tell is that how to calculate the defect formation energy is just basically we calculate the total energy of the perfect lattice and the defective lattice, and then we compare the difference, taking into account the defect and chemical potential. Because this type of material are actually ionic, that means when we take the defect out or put defect in, we also introduce extra charges. So we also make sure to correct this electron chemical potential. And of course in DFT we do our best to simulate a realistic cell, but after all the cell is still small, and we make sure we do some corrections to do our best to get an accurate result. Just use MAPI as an example. This diagram may be a bit more complex, but what it actually means is this formation energies as a function of the Fermi level. And you see the slopes, the positive and negative slopes, because some of the ions are positively charged, some others are negatively charged. And the charge neutral condition makes sure we actually find the intrinsic Fermi level. And the energies, the defects that are lower in this diagram, they have low formation energy. This means, in this case, the MAPI, MA interstitial is the most abundant and is compensated by oppositely charged vacancy level and L interstitial. If we look at these three defects in the electronic band diagram, which I highlighted them here, and you notice all of them, although there are a lot of them, all of them actually landed on the band edge. This really means they don't cause any electronic disruption. At the typical concentrations we get on the table here, I actually qualitatively agree with experimental observation quite well. This means that there are a lot of defects, but they are not directly harmful for the electronic properties. Why is that? To intuitively understand this, it's important to compare to the traditional semiconductor, to also understand how the electronic band structure form. Basically, when we make compounds, the electronic structure is the hybridization of their atomic levels. They form bonding, anti-bonding, or complicated interactions, give you many, many different bands. And if you look at these two types of semiconductor, their band character are totally different. If we have an extra atom or we have a missing atom, this means a disruption of these atomic levels, and we will create levels nearby these levels. And if you look at carefully, that exactly because the intrinsic electronic structure of the halide perovskites made sure, even though a lot of defects are there, but the defect level actually landed in the bands or on the edge. This is exactly the fundamental reason why the defects are not harmful for the efficiency directly. But this is not the end of the story. We know this type of material are soft and also they're easy to make. They're very dynamical. This dynamic property is very, very fascinating for me as a theorist to look at, but they also cause a problem for our solar cells. That means under stress, under light, electric bias, thermal or chemical stress, degradation happens. To look at this type of properties, we need a totally different set of tools, which we need to build it on our quantum calculation. That means we need to get accurate interaction potentials for the new species. In the past years, we have explored the different kinds of methodology. The philosophy of developing this method is basically we start with either very accurate quantum calculation data or from experimental data. We do iterative training until our force field, our potential produce accurate DFT or experiments. And then we use that to do large-scale molecular dynamic simulations. One of the characteristic property of perovskites is phase transition as a function of temperature. So we take advantage of this property to actually validate our models. This is data, experimental data, and as you can see, we explored 3 different methodologies. All of them qualitatively capture this dynamical property, and the more expensive methods are more accurate, but we cannot do a lot of simulation. This method describes electronic and ionic interaction at the same time. Machine learning is also very accurate, but here we only learn what we see. That means we only can use the force field to simulate the system we trained on. And more empirical methods allow us to put in a lot of intuition on the chemistry. That means they are chemically transferable. You can study a class of material, but they are slightly less accurate. Today's focus is on the degradation, so I'm going to show the application of this method because this method allows us to look at the severe dynamic processes like degradation. So we experimented with these 2 typical defects again, vacancy or interstitial. We find both of the ions are extremely mobile. They travel around in the lattice all the time in the picoseconds of frequency. Vacancy, interstitial does not do much, but vacancy, if you see after a few nanoseconds, we actually get a degradation product like an amorphous lead iodide layer. This layer becomes photoinactive, and you will lose the efficiency of the cells, of course. And these spots actually can nicely correspond to the sun image we are showing here. So this is a point defect. What about more extreme defect like surface, grain boundary? We did the same simulation on the slab. This is a cesium lead iodide with 2 totally different terminations. If you look carefully, the top surface behaves totally different than the bottom surface, which the top surface, I will give you already the result while you look at the atoms. The top surface totally become an atom soup, and the bottom surface are wholly stable and remain intact. What's the main difference between these 2 surfaces? If we look carefully on the top surface here, we are missing an extra iodide bond that is bonded to lead. That's one thing. Another thing that this green sphere is a cesium ion. We don't have that. So basically these 2 features, missing an iodide bond is actually really missing a covalent real chemical bonds. Make this surface vulnerable. The iodide starts to be mobile, and there's cascade of more dynamical process going on, and then the lattice eventually has been destroyed. Another advantage of this surface is this cesium. The cesium also does not form a covalent bond, but it's big atom, it's heavy, and it has electrostatic interaction. The most importantly, it holds the iodide here, does not allow it to move around. This is very, very important to stabilize this surface as well. So use this very simple system model, we get this understanding where this chemical instability comes from. Now you can guess next what we do. So we're going to try to pathway them. In order to get very efficient passivation, we need to look at the chemistry a little bit. This you see some lead L as example again. So we need to find chemical species form strong one with lead, but also with iodine. If you look at the other side of the periodic table, the species that can form strong bonds with lead are this corner, And if you look at this side, the species could go to the lattice, form a strong electrostatic interaction is on this side. And indeed, I'm going to show you a few examples of how did we do this. The first case is incorporating a little bit of fluoride in the cells. Fluoride is the smallest atom, except hydrogen, of course, has the most electronegativity, and therefore, when we make the cells, we put a little bit of additive of this. Because it's small, it induces lattice strain inside, so it goes onto the surface. Once it goes on the surface, it forms all a strong bond with everything on the surface, form passivation of every species up here. As a consequence, we actually get a slightly bit more stability in the solar cells. Okay, the next example containing oxygen species, this time it's a big molecular, a cation. Again, this does not go to the bulk because it's too big, it comes to the surface. They form different bonds, this time oxygen lead and also oxygen with hydrogen bonds. It gives a similar increase in the stability. Okay, another molecule that has even more complicated. This molecule has oxygen species as well, but it has 3 arms. This is very interesting, and it's been applied in the interface of the cells. What it does is it does several things together. When you put it on the tin oxide, on the one hand, it passes its oxygen vacancy on the tin oxide. On the other hand, they also tune the energy level alignments between these 2 layers. And if you pay attention to this small umbrella, it actually, all of them nicely form a layer on top of tin oxide. When we grow perovskites on top of here, we grow a very nice homogeneous film. That's potentially reduce the defect. And by doing this additive actually altogether make the cells more efficient and more stable. The similar things happens in LED, but there the electrical bias, the electrical stimulation is the worst enemy for us. That means we have to immobilize the mobile ions. We do the similar kind of strategy. This time we put more small inorganic cations. These cations are very interesting. Cesium is just big enough to go to the bulk. Rubidium is a little smaller. It goes a little bit on the green boundary. If we do put a little bit of both in there, that means together they immobilize the film everywhere. The same story, a bit like following the solar cells here. We can do this using a large molecule as well. This molecule has a kind of a bit like act like the cesium, as I just mentioned. But now it's longer, and its handleness for this aerodynamic movement is even more pronounced. Again, another molecule with 2 heads, and this molecule is interestingly the thermodynamic just allow it be in the film but not in the bulk. It landed on the green boundary. And this is relax the strain between different grains. The relaxation allows a bit of stronger passivation of the air and the atoms around. As a result, all the LED devices obtain a slightly increased stability, operation stability. Okay, I think I have enough example I showed you about the stability, how to passivate the films. But so far, we're only looking at how do the passivation effect. But we forgot one effect is that when we make the film, all the things we already added in the beginning. That means all the chemical interaction we were just mentioning also impact how the film grows. And you can see this is exactly some of the examples I showed above. By adding a little bit of different chemicals, you grow totally different films. This means fundamentally to stabilize this type of material, it actually lies on how to grow perfect crystals without the defect, how to actually optimize the growth. In order to do that, indeed this is a new project that granted a Wiebke grant, that we use the similar set of tools, we used before, but now to look at the growth. From atomic level, how precursors interact with solvents, how do they form intermediate molecular cluster and a crystal. If we are able to track this, we'll be able to understand where and how defect form. And then it allows us to play all the processing parameters, the chemistry, the temperature, the substrate, the dimensionality of the film. A lot of new research, but also possibility opens up. To do this, the most important, it's actually more challenging than you guys would imagine, because in the lab, when you make the film a few seconds, you get a nice film, but in the simulation, which minutes, days, months, this is a very slow process. So we need actually a lot of methodology advancement here to be able to simulate that. The most important is to get accurate potentials, and also to push the slow reaction to actually stage it in the simulation. To do this, we need a lot of collaboration with our experimental colleagues to actually help us to develop model, but also validate them. This is very challenging, so I hope 5 years later I can show you exactly a beautiful crystal I can simulate. But now I'll show you just some small examples what we worked on. The first example is the role of solvents in the growth. Typically, we know that in the lab, there are two very popular solvents, DMSO, DMF. They are added to make the film, and the ratio of them, how do we add it, impact the film formation, in a way that the solvents actually interact with the lead species in competition with the aldehyde interaction. The stronger interaction the solvent has with lead, that means the slower growth, and the opposite is true as well. By understanding this, we can actually see in DMF, they quickly grow a very a cluster, but it's not very nicely 3D. But in DMSO, you have the opposite. The bond is so strong, you grow a very small cluster. It does not form 3D. When you mix both a little bit, you just get the best balance in the kinetics. So the second small example is in the cesium lead iodide, we play the precursor ratios. If we make the precursor a little bit of cesium rich, we actually tend to get a black phase film that is good for the solar cells. And what is happening there, if we do the simulation, this atom soup is a little difficult to say, but you will notice something. If we plot the RDF, you notice a little bit of cesium is very helpful to form 3D-like nucleation. And this promotes the growth of the black film. Okay, last example. And this is a cesium compound with mixed L and bromine. This is a nanocrystal made in the lab with quenching and needing a lot of extreme ultra-equilibrium growth condition. One interesting thing about the growth is that we actually, in the high resolution TM or STM image, we see a RP kind of defect. That means the lead L, the planar bit shifted, and this defect are terminated by cesium iodide or cesium bromine termination. What is interesting about it is that this film allows us to obtain discrete domains that give discrete emission or absorption that allows us to manipulate this purity in this for quantum application. Why is that? Is the most important question. Why we can grow a domain with discrete iodide bromine distribution? So we did some simple simulation again. If you remember, we had a simulation of this for the degradation simulation. This termination is very stable. It did not degrade, it is staying intact. And in this case, it's the same. But if we take into account the defect inside the grain, we want to see if the defect will migrate across the grain. If we do this simulation, you actually see no matter where we start the defect, they go nowhere but stay in the domain. That means once your film forms, once you have the RP domain, the composition is nanodomain are protected, and it's always having the same emission peak. This simple simulation demonstrates this effect. Okay, how much time do we have? Yeah. Okay. I was rushing a bit because I was also excited to want to show you a little bit more. So I have 5 minutes, so I can do that. All the tools we have, all the simulations that we have done, I showed you, it's on solar cells. the same fundamental understanding of the same chemistry physics can actually be applied to other applications. There are many other new optoelectronic properties we can study. These involve light, charge, spin, and everything. And so again, we use perovskite as an example. So all the perovskite we showed just before are 3D dimensional. They have small carton just fit in the octaedral. If we use different ligands, or we play with the chemistry, we can actually get 2D, 1D quantum dots. With the expansion of the organic chemistry, you get all different kinds of ligands. In this case, it's very interesting. These ligands are chiral. Chiral means like our hand left and right-handed. And these ligands give very interesting property because it gives induced asymmetry in the lattice. This actually causes band splitting. That means it gives rise to extremely interesting spin magnetic properties. And on the other hand, this chiral molecular or this chiral geometry actually also have chiral opto activity. This allows us to actually detect or absorb left or right-handed lights. The combination of this interesting property gives us many interesting new physics to study in spintronics, in photonics, for information application of quantum materials. And we can use the same set of tools to look at it. But this time the focus is more on the quantum side, because now we're more putting all the effort on the how charge and how light interact. And as you see, these crystals beautiful and very interesting, but they're so big for us to simulate. That means we could go deeper to more deeper theory to incorporate all the complicated theory, but we cannot do that. And in order to do that, we combine different sets of tools. Actually use DFT as starting point, get wave function. We build a Ted banding model to incorporate the chemistry, the electronic properties there. In this model, we can simulate large structures. We can simulate many different structures, and we plug in all the sophisticated theory, like to look at excitons, to look at spin splitting effect. Also, ultimately, to actually translate this electronic or optical interaction to transport models to allow us to design novel devices. Again, this is very new. I've just shown some very interesting but not conclusive preliminary results. By changing the ligands in this two-dimensional lattice from a bit of a linear to with a ring, and the ring with a tail. This tail is chloride, a bit like the fluoride this morning showed. This kind of cation, when they go into the lattice, because their chemistry, because their geometry are different, they induce different distortion to the lattice. That means they can induce different splits in these bands and give different spin splitting. So we were wondering whether this has a correlation with the size of this left and right absorbance of light. So we can see, indeed, if you compare two of them, the band split are different, but the CD character are not so different. But for this totally different, a bit of new species, we get a huge response here. So we understand something, but it's not the complete picture. What can I tell you more? That's all. So I hope in a couple of years I can tell you more about this new physics, because there are many open questions. I would like just to conclude to say that indeed defect is very important for semiconductors, and in particular halide perovskites, the defects are not directly harmful for the electronic structure. However, in the material, in the chemistry, there are so many things are moving, lattice moving, ions are moving. They do complicated things with light, with electrical bias, and they give us a lot of interesting physics to study, but a lot of inconvenience for the solar cells. Therefore, understanding them is very important. But in the end, to actually grow a film or to actually make a stable cell, we need to get rid of all the defects, really to actually try to synthesize the most stable material without defect. Then the growth, the chemistry become very important. And I hope I also showed you that this fundamental study in this atomic or molecular level is actually very much complementary to the experiments and to get more insights, and every understanding push a little bit on the stability. I hope together with the community we contribute a lot in the next few years. Indeed, the efficiency, we don't worry about it, and with all our effort, I hope in a couple of years we can push this to there, and then maybe on the roof. With this, I'm finished, but I want to thank a few people. These are all the students worked with me in the past years, from bachelor to master to postdoc to PhD. Not all of them are there. We had a lot of fun and a lot of challenge to overcome together. Also a few of my computational material science experts, and they are experts in different kind of methodology. We enjoy so much to discuss the methodology but apply it on different topics. The last but not least is our experimental colleagues. You ask me very interesting questions, stimulate me to think, but also allow me to feel my work is more useful and making more impact. Thank you very much for your attention.
Okay, fantastic. Thank you for that very nice talk. I think we have plenty of time for questions. Let's see, we have one here in the back.
Thanks for a really nice talk. I was actually very intrigued by the work that you've done in crystal growth. It was nice that you showed that DMS and DMSO have different crystal growth rates, but I little bit know that maybe it is due to the complexation how they form. Do you also plan to simulate how these complexes evolve in a time scale? Okay.
Yeah, thank you very much. It's a really very relevant question. Indeed, so today I only showed a few examples just to simplify what I'm showing you already very overwhelming, a lot of atoms. But indeed, so exactly the atomic level, what happens, we are also particularly interested in the molecular level, what kind of intermediate molecular cluster, also molecular solid phase, geophase, as we call it. It's not totally solid. So we do have a few work on that, a bit preliminary insight on that. But I have to admit that we rely a lot on experimental input as well to give us the initial insights, what's the possibility. So for that we have some interaction with Groep who has Defects. You can in situ monitor this crystal growth and can see different clusters. And this is really helpful, yeah.
Okay, more questions? Yeah.
Thank you very much for such an inspiring overview. I actually have two questions, but I'd be happy to continue the discussion later. First, in the analysis of the role of different solvents in the behavior of these systems, I wonder if you can comment on the role of water in these the water. Yes, in these systems when analyzing also the solvent effects, including these that normally come with certain water content.
Yes. This is an extremely interesting question. So I read in non-simulated water, but from what I read in the literature, I say water has quite different roles in there. Indeed, the oxidant from water can coordinate with lead. Some groups from very preliminary results say that this could slow down the crystallization, help for grow a nice crystal. But some others would say when you form a cluster or intermediate species, the water is actually contamination or degradation precursor, and water-induced MA deprotonation. So it's more complicated than just one thing. I hope this is
it seems quite contrasting in use. So I would be curious how your methods could contribute to maybe assessing this. And maybe just a brief question. Could you comment on whether any of these methodologies have the potential to contribute to assessing the mechanical stability of these materials?
Yeah. So for example, if you talk about mechanical property, let's see some lead air. If you want to apply pressure on it, you can look how the lattice dissolved as what kind of phases it has. Yeah, totally. Yeah.
Thank you very much. Happy to discuss further.
Hello, thank you for a nice talk. I have it's a bit out there, but I was wondering what we see a lot now is that for these double cation, double halide, or double cation, triple halide compositions, that by now people make films with slightly tiny grain size, and that doesn't seem to be too bad for the optoelectronic properties. But then what you also see is that over time, under all kind of influences, the grain size will, for example, grows. And I think like under electrical bias, under all kind of different biases. And I was wondering if your simulations could show if you're in some kind of metastable situation, right? Because it seems to be that kinetically from the how you grow them, you can make a nice material, but then over time it's anyhow still sort of somehow trying to form a more stable film. Is that something you know something about or could maybe do in the future? Because I guess the double cation is still a bit hard to simulate.
Yeah, so this is a very interesting question. And I think you have many layers of question in this one question. If you tune the chemistry, the double cation or triple cation or even mix the highlights, of course, if you assume all of them go to film, they will form a different structure that has itself has different kind of stability already. Another side is when you grow them, depending on the ligands, how do they interact? You can grow slowly or quickly. We grow more homogeneous or less homogeneous. Even if you grow a film in the lab, and if you put in a solar cell, it still constantly evolves with the light, with the electrical bias. What I'm saying is nothing is static. Everything are moving all the time. So everything has to be taken into account. And for us, we can simulate each of the different stages. To get everything together, we need the whole field. Different kinds of characterization, electrical, optical, structure, DFT or MD, everything. So that's why we need everybody. Yeah.
Yeah, thanks, okay. Wonderful talk. So I really like your simulation where you talk about the grain boundaries. So I was wondering, did you also put the substrate already? And
yeah, so not yet. So we use Wiebke as a model system to develop our model. Of course, when that is done, because there are a lot of data there, we know a little better. Of course, the most realistic or the most industry relevant is to grow on the subject, to grow in the device. That's the next step. That don't mean they're difficult to simulate if we just don't have the parameters. So we have to develop them. The interaction with different material are new, we have to develop the parameters.
Okay.
Yeah.
So because then I was wondering, could you see in your case it's really surface dependent, right? Termination dependent.
Yeah.
But then you have a substrate, and then if you have two grains next to each other, then you have many interfaces to simulate.
Yes.
So that's expensive, I guess, in terms of calculations.
It is. Again, we can chop this problem to different species. We look at the beginning, we look at so we need the experiments as well. You tell us what is perhaps happening here, what is happening maybe in the end. We can tackle each piece of puzzle in the end.
Separately.
Maybe hopefully we get the whole picture. Yeah.
Thanks.
Okay. Well, very exciting talk. I was wondering if you would be able to also simulate kinetic effects, because I saw that you'd have a time scale on your simulations.
Yeah.
But then very often when, for instance, you grow nanocrystals, what you get in the end is not really the thermodynamically stable product, but it's just a metastable situation in which you drive that just kinetically.
Yeah.
Would you be able to also modulate or estimate the different kinetics of different processes?
Yeah, absolutely. So the parameter we tune there is the temperature. So you can increase the temperature or make it very low and see how the kinetics change. What kind of species first form if you have your annealing condition or if you are annealing it differently. Yeah.
Okay.
Also the kinetics applies to when you apply different chemistry, the kinetics are different as well. Because you actually overcome different kinds of barriers each time. Yeah.
Maybe a related question to the input from experiments.
Yeah.
So I guess you use the quantum mechanical DFT calculations to get as close as possible description of the interatomic potential that you then feed into your molecular dynamics simulation.
Yeah.
So how can you validate the correctness of these interatomic potentials from experimental input? So what is the key result that you like to see? Because I think that is the game here.
Yeah. So what I showed for the simple growth or lattice dynamics, we validated with the phase transition. They see similar all day from change phase from low temperature to high temperature to qubit, or something catastrophic qubit. This is a typical thing we could validate. Of course, if you look at different problems, we'll find similar kinds of validation. And another validation is to validate to more accurate methods. So if we know we produce a more accurate method, then we are more or less happy okay, it's doing the job.
I see.
Yeah.
Really nice talk. I really enjoyed it. I was just wondering, you showed some passivation molecules. So can you predict, for example, if you have a lead halide terminated or organic terminated surface, which type of molecules will be better to use?
Yes, so it's a very interesting question. For the first hand, we actually don't know what termination will get if you apply a passivation. So that maybe is already first question. Because when you add an additive, we can promote particular surface to grow or promote particular termination. So it's actually the question I reverse. Does this make sense?
But then, for example, if I tell you, okay, I have organic terminated surface, can you tell me which molecules will be better to use?
Yeah. So you can guess a little bit because indeed what you expose to the surface is lead and halide. You just would say what interact with lead strongly. That's how you choose. This is exactly the species on the right hand side of the periodic table. Oxygen, the functional group, fluoride, chloride. All the atoms have slight electronegativity compared to halide. They bond to lead more stronger. This, of course, choosing this is not only that they have this species. I'm going to choose it. There are a lot of chemistry involved as well. Whether the solubility in the solution, the availability of a particular molecule, there are many factors are in there. Whether the species are toxic or are mostly available, economic consideration. There are lots of consideration in this, of course.
Okay, let's thank Shuxia again for this great talk.